All right, so we're going to start with Article 210 out of the code book. So I'm gonna try to make this fun because, to be honest, code is boring. Can be boring to just go through law after law after law that the code book is telling us about. So I'm gonna try to make this as entertaining in a way as possible, just so we're not lost and stuff. So I might pause here and there to just ask questions. So be ready to field questions as I get to know names better. I'll be picking people out that I might want to select for reasons or others. For now, I'm just gonna go with my gut on a name that I may ask a question on. So keep that in mind in case I call your name. Just be ready to field the question as we, because I don't want it just this to be endless talking with endless highlighting, and then, a lot of things can get missed that way. So let's start with what are the main topics of Article 210? Feel free to write this down. I am going to be also saying things like that. Write this down, write that down. Don't write this down, or like what I just said, feel free to write it down if you want. Not as important because we're just going to eventually go through all of this, but this is kind of a bullet point on everything that's going to be covered out of Article 210. This is why I say this is a big article. As you can see, this is like everything for the most part in a residential. The only thing this doesn't cover is two things. One, what size panel does this house have to have with all of these things in it? And two, what size wires do I need for all of this stuff? And those will be covered in the articles in the 210 and 310, weeks 3 and weeks 4. Those are two other big articles. So 210 and 215, the ones we're going to cover this week 1 and 2. And you'll notice I just set aside the conduit ones. We'll hit those conduit ones as needed, only because you're also going to be working with them in the labs, and you'll know what we're talking about once you've worked with them for a while. It's also why I put it on the back end of this first 2 weeks. So number 1, multi-wire branch circuits, and we'll just run through this quickly and then we'll get into the stuff. Number 2 is GFCI and AFCI protection. All right, both of those, if you don't know what that means, this is ground fault, circuit interrupting. This is the one that protects during a short circuit or a ground fault. Even though they call it ground fault circuit interrupting, it's also a short circuit interrupting, which those two are two different things. You will get to this in Code D when you get into troubleshooting, which maybe I'll be your instructor or not, don't know. But a short circuit happens when the hot, the ungrounded conductor, and the neutral, the grounded conductor, come into contact with each other. This is considered a short circuit because the circuit is leaving a breaker, going to the load, and then returning back on the neutral. Let's just put 20 amps for that breaker. This is a circuit. The only thing that's stopping the hot and the neutral from touching is the load. The load has resistance. So this is why the hot and the neutral that both go to the light bulb don't have a short circuit yet. If I got rid of the load and bypassed it in some way, now I've shortened the route of the circuit. This is why they call it a short circuit. Basically what happens in a short circuit is resistance drops to 0, amperage inversely proportional skyrockets, some crazy numbers start to apply, like 10,000, 20,000, 30,000 amps go into this basic 20 amp circuit. The ground fault is different. The ground fault has no circuit issue because the ground and the hot do not make a circuit. They do not complete a circuit. The ground is only there to protect. Actually, let me bring that back and use it. I have my ground also in the panel, and that ground also goes to the load. This is not a circuit, that's why they don't call it a short circuit. If the hot and the ground, let me use yellow. Sometimes it's a little bit hard to see yellow. Let me know if it's hard to see yellow. But if the hot and the ground come into contact, this is a ground fault. All right, so just two terms. You don't have to write those down. It'll be in the video if you wanted to go back and look at all of that. This will be something you'll cover in later modules. But just to keep in mind, because the word is there, GFCI. The idea of a GFCI is to do the job that the breaker does, except faster. That's all it does. Ground fault circuit interrupter, or GFCI, or GFI. A lot of people don't, they cut out the C, just easier to say. GFI is the same as a breaker. A breaker will trip if there's a short circuit or if there is a ground fault. The breaker will trip. It'll shut off the circuit. But that takes about 1 second to 2 seconds for the breaker to trip during a short circuit or a ground fault. Because the situation, like a short circuit or a ground fault, could involve a person getting shocked, then the GFCI made it so that the response time went from a second or two, which doesn't seem like a lot, but if you're getting shocked, it is, to about half a second. So 0.5 seconds is how fast, even less, a GFCI will trip. And the reason being is just distance. All right, the GFCI has the thing plugged into it, right? The load is plugged into the GFCI versus the load plugging into a regular outlet, the regular outlet going all the way back to the panel. Electricity travels very fast, but this is still going to take time. And there's still resistance in the circuit. So it's hard even, we're going to get to, in this Article 210, this thing we call voltage drop, which is, I lose voltage the further away the thing that is being plugged into this circuit is. If it's 5 feet away, I don't lose any voltage. 120 starts at the breaker, 120 ends up at the outlet. But if that outlet is 300 feet away, 120 starts at the breaker, I might have 98 volts at the outlet. So we got to compensate for that. This same effect, which is resistance, or distance equals resistance, the further away something is, the more resistance the circuit has, happens in the same way if we're trying to turn off the circuit during a short circuit or a ground fault. The further away the problem is to the breaker, the longer the breaker takes to react. So for this reason, the GFCI in residential is going to be very mandatory in some locations where water is involved, where people can potentially be working with high voltage things like the garage and stuff like that. So we'll get to that. But different from arc fault. Arc fault protection is only at the outlet or the breaker these days. You can have either one. Same thing with a GFCI. You can have either one, a GFCI breaker or a GFCI outlet. But the GFCI breaker, in my opinion, and in the opinion of most inspectors, defeats the purpose that I just talked about. The GFCI breaker is still at the breaker panel now. So the distance is still a problem. So, a lot of people get away with it because it satisfies the code. But I've had inspectors tell me, no, get rid of the breaker, put the outlet because response time. So AFCI, same thing, arc fault, circuit interrupter, and this prevents arcing. This is something new, by the way. This wasn't a thing when I was coming up. Arc fault was not a concern. Somewhere along the lines, it became a concern. What is arc? What is an arc fault? Well, arcing happens when you unplug something that you didn't turn off. Right? It's a real easy explanation of what arcing is. Because let's put an outlet, right? I got something plugged into this outlet, whatever load there is, and it's on, meaning it has amperage now. It is creating current when the load is on. All right, something that if you weren't aware of is something to become aware of. An outlet doesn't have amperage. It doesn't even have wattage. It just provides voltage. So the outlet just has 120 available. When you plug something in and turn it on, can't just be plugged in because it could be off. When you turn it on, now Ohm's law happens. Voltage, resistance creates amperage, creates wattage. All right, the load has the resistance. It just got given some voltage, and now Ohm's law. So because the load has amperage, let's just say 10 amps for easy numbers here, it is now making the connection between these 2 points. The current is running now between the wire that you have plugged into the outlet. If you were to simply pull that cord now with the load on, you are now separating 2 points where current was enjoying the ride. And as you're pulling away, current is like, hold on, I was still going that way. And that's what that little arc between these 2 points is. It happens only if that load is on. If you turn this off and no longer do I have the connection, no longer do I have amperage, I still have resistance and voltage, unplug and plug in, no arcing. So because homes, right? People, homes, carelessness, you can't tell somebody, hey, don't forget to turn that lamp off before you unplug it. Everybody just yanks the cord. Arcing happens every single time a load is on and gets unplugged. And it's in outlets because, you know, the laundry machine, or not the laundry, but the oven could possibly be unplugged, but nobody's unplugging an oven or anything like that. People are unplugging computers, lamps, things like that. So arcing happens. Arcing can potentially cause fires. And so these arc fault protection breakers, which we'll talk about, protect the circuits during those events. All right. The other stuff is just going to be things that we'll get into in the code. There was some stuff to break down here in the beginning, which we'll get into a couple more things. But how many branch circuits can I put into a particular breaker, right? How many can I put under one breaker? How many branch circuits do we get in a panel? We'll also cover overcurrent OCPD, which I'll talk a little bit about that specific thing in a couple of slides over. But how big does the breaker have to be? That is something that we'll cover as well in this article. And then location and spacing. This is general receptacle and kitchen countertop spacing. There is a requirement. Although a lot of older homes, a lot of older apartments don't have these things, if you do new construction, you do have to concern yourself with location of outlets. You have to have X amount of outlets in a room. It is based off of the dimension of the room, how big the walls are, how close to the door the outlets, and all of this is cord related. All right, this is why they space the outlets in a particular way, is because the cords are a specific length. For example, lamps and things like that, TVs, things like that, they come generally with a 6-foot cord. So that's kind of the spacing for outlets in a wall. 6 feet, and then when we get to a corner, it becomes 12. We'll get into all the dimensions, not to get too deep into that right now. Different from counters. The countertop and things that go on the countertop have a shorter cord, 3 feet. Blender, microwaves, things like that. You'll notice, and now you can do that experiment if you want. Go to those components. Washing machine, long cord. Microwave, short cord. And so the spacing is different on countertops because of the appliances that go on the countertop. I can close that, that's the attendance. Well, no, I wanted to call it. And then we'll get into general lighting, which we'll unpack what that means. General lighting is just general purpose receptacles. I know it says lights, but that's what the code book calls it. General lighting is your general purpose receptacles and then your general purpose lights. In other words, the receptacles that don't do anything until you plug something into it, like the ones in your living room, they don't have a job until you plug something in. Different from your washing machine receptacle. That one is for or laundry room they call it. That one is for the washing machine. Or the dryer receptacle. That one is for the dryer. So general, meaning stuff in the bedroom and hallways and things like that.
Question.
Yeah, go for it. I was about to just ask that right there.
Is the 7 just like a typo, or because you have
Whoa. What happened to my brain on that one? I must have been thinking 7 for a reason. What a great catch. Thank you, sir. All right, 6. Thank you. That's on video now. Forever in there. All right, anything other than that that you want to follow up with a question? All right, cool. So let's start with some questions that I will answer for you. Because does everyone know what this is? Does everyone know what that is? Does everyone know what this is? Not yet, maybe, or probably, or maybe not. So we'll unpack all of these. All right. So this is, and I'm going to head over to the code book now. If you guys want to join me, we will highlight a few things, so definitely get there at some point. I'm going to run through a lot of this and then fall back. We're only going to be on the first page of the code, article 210, which I have here, and it's on page 78 if you want to head over there. All right. We will reference a few things. First, we want to get through a few definitions, or I want to get through a few definitions, and then we will point out where we have the article that supports what I'll be saying and to highlight it. But right now, the only thing to focus on is just that word. All right, this is an article that covers branch circuits. All right, as you can now just focus on the scope for a second, which doesn't tell us much. All right, this doesn't break down anything for us. We will have to break down a few things here. But it says this article provides the general requirements for branch circuits. Not over 1,000 volts AC, which is a lot. All right, that's a lot. That's every volt that we worry about. And 1,500 volts DC. All right. And the reason that 1,500 volts DC is now showing up into our lives is because of solar panels. All right. This again used to not be something that was around as much when I was coming up. We only had the first part of this, but now DC is very much involved in a lot of residential, especially you guys in California, because solar is so good in California. Solar is like one of those geographical things. If you can have solar, anyone can have solar. The sun's always out at some point. But if you live, for example, in northern Alaska, you don't have the sun for like 4 or 5 months. So you want other means of secondary energy. But that's what that means. That's why 1,500 volts DC is around. So let's pause there. All right, let's break down what a branch circuit is. Because we're going to have another article in this second week. Maybe we'll get started on Friday to see how we get through the week. That's going to cover feeders. That's a different set of wires or conductors or circuit. So what is a branch circuit? Definitely, and this is one you're going to want to write down. And there's a lot of variations of this particular definition, but this is about what everyone is going to tell you. A branch circuit is a circuit that originates, by the way, call me out on any misspellings or anything like that I forgot, 7 to 6. Originates at the final, I'm going to highlight that for a second because we're going to talk about that. Overcurrent protection device and ends where the load is connected. All right, as far as the load being connected, any method that we use to connect loads to the circuit. A very easy method is provide an outlet where somebody can plug something in. But not all things are plug-in ready. Things like motors and machinery is not plug-in ready in some cases. Some machines are, some machines are not. Right? If you have an outside air conditioner, a central air conditioning and heating unit, or HVAC they call it, then that is not a plug-in to the outlet system. That is a hardwired system. Whereas if you have a window air conditioner, that does get plugged in, and so that would be considered a different style air conditioning system. One gets plugged in, one gets hardwired. So keep that in mind. Loads can be connected in many different ways, all right, to the circuit. The reason why they say final over current protection device, let's break that down all the way to first, what are we even talking about? A panel, all right? Here is my panel. Panels have two lugs that bring in, we'll just do a residential panel for now. We won't get into the phases yet. But it brings in the hot and it brings in the other hot into the panel. All right. We also get a neutral into the panel, which I will make in blue here. So this is our panel. And this is where our OCPDs are, our overcurrent protection device. All right. I will have in a second a breakdown of that, but since we're already there, let's just take a look at it. Don't have to write it yet because I'm going to bounce right back to the other one. However, what I'm talking about as far as overcurrent protection device is a fuse or a breaker. All right, coming right back over. We'll be back to that. In most cases, we will just kind of default talk breaker, but when you get into industrial settings, machines don't have breakers sometimes. They have fuses that protect them because they have motors, and motors go up and down with their amperage, and breakers can be a little bit more sensitive and trip when a motor is just starting or operating, whereas fuses can withstand that. So here's our breaker. But let me set up two systems here for us. I'm going to actually do this another way. All right, we'll put a little 20 amp breaker here. And then I'm going to put a 2-pole breaker, all right, where we have A phase and B phase. So this breaker is heading over to an outlet. However, this breaker is feeding the sub panel in the garage. All right, very common to find these in homes where you have a sub panel. If you get into a commercial building, then every panel you put your hands on is going to be a sub panel because there's one giant 2,000 amp main distribution panel that there's no reason to ever go into that monster. All right, you're always at the subs in a commercial and industrial building as well. One of these is a branch circuit. One of these is not a branch circuit. All right. This one is a branch circuit. This set of conductors is not a branch circuit. That set of conductors are feeders, which we'll get to in Article 215. Because as I was drawing this out, I even used the term. This breaker is feeding power to a sub-panel. Whereas the one on the top with the receptacle is meeting the definition of originating at the final overcurrent protection device and ending where the load is, because that's all there is to this particular circuit. Whereas with a sub-panel, I'll just erase now that name, we might have another breaker here, and I'm just going to slide this up because I realize sometimes the bottom right can be annoying to see, where we head over to an outlet, and now that becomes our branch circuit, because now we're meeting the requirements of the definition. Originating at the final, this is now the final overcurrent protection device, and ending where the load will be connected. All right, and this is where general purpose and purpose outlets come into play. I don't know what's going to be plugged into this general purpose outlet, so I'm going to make some assumptions about the size of the breakers that cover those. This is where OCPD rating comes in. From this one down here, 4, we'll be sizing that stuff. Versus if this was, let's say, going to be the dryer, then I do know what size that's going to be, but not to get too far ahead. All right, I'll pause there for a second. So keep that in mind. All right, if you see an image where you have a sub-panel, the sub-panel wires or the wires going to the sub-panel is not going to be our branch circuit yet. From there, whatever is being fed off of that panel, those will be considered branch circuits. All right, so as the definition says, final overcurrent protection device. A little bit annoying sometimes that it says final overcurrent protection device sometimes. It should just say overcurrent protection device. But because of the fact that there could be sub-panels, then that's why they specifically put it that way.
Yeah, what are the arrows?
The arrows is me just pointing to the particular ones versus the other. So, yeah, as far as this wire right here, I'm just pointing at those, that arrow is pointing at the wires going to that receptacle. This arrow is pointing to the wires going to that sub-panel. Same thing going on over here. And this one was just pointing at a breaker. All right, any follow-up questions so far? Okay. Get rid of this. By the way, again, all this is on video, so if you wanted to see any of that. So let's say we have a situation in which I have a panel, I have a breaker, all right, say 20 amp breaker. I go to a light switch. From there, we pick up, this is our light, which I'll draw like this. And then I have an outlet over here. Okay, so now I'll ask some questions. I'm not going to signal out anybody right now. I'm just going to open this to anyone who wants to answer it. And please feel free to just answer it. No hands have to go up. Is this conductor here considered branch circuit or not?
No.
Okay. Is this one here heading to that load considered a branch circuit? And by the same question, the one going to the outlet?
Yes.
Okay. So there is where I wanted to break something down a little bit, because switches are a little bit of an annoying feature, not in the sense that they're annoying, just in the definition up here of originating at the OCPD and ending where the load is connected. Switches are just a means of opening and closing the circuit. If you want to write that down, go ahead, but that's all the switch is going to do. The switch is going to open, turn off, right? We call it opening the circuit when we turn something off, and close when we want to turn the circuit on. All right, so opening the circuit is off, closing the circuit is on. The switch does not change the fact that this entire thing, and I know you guys were thinking in the right direction, because why would this be considered a branch circuit if it is not ending where the load is connected? But because the switch only opens and closes the circuit leading to the load, a switch becomes part of the branch circuit, even though, again, it is not ending where the load is connected. So I'm going to, unless anybody wants to draw this out, I'm going to add that as a note, giving a little bit of time here for any pictures that you guys want to take, and just give you the note now that I'm going to write. All right, the switch does not interrupt the branch circuit. The switch is part of the branch circuit.
Excuse me?
Say that again.
So the receptacle on the bottom is not a part of it then?
No, the receptacle is, so in other words, this entire thing, leaving this breaker right now, is a branch circuit. The whole thing is a branch circuit.
Okay, you didn't highlight it, so I was like, is it not included or is it?
Yeah, sorry about that. You're right. I only went to the load of the light itself. Yes. So this one as well becomes, the whole thing becomes the branch circuit. In other words, the wires leaving this breaker at this point are already branch circuit conductors heading over to the switch, pigtailing and grabbing this outlet, and then the ones heading to the light as well. The switch only opens and closes the circuit, but it is part of the branch circuit. Right? So that's the note I'm going to write. The switch is part of, or a switch, we can just call it a switch, is part of a branch circuit. So let me write that note here, and then I'm going to mess all of that up. A switch all right, a switch is part of the branch circuit. Even though, again, it is not technically where the load is connected. So just a little bit of a twist to that one rule there. Okay. Now I'm going to show you a switch that kind of messes this rule up a little bit. All right. Good thing about having the online setup is I get to go online. So here's a switch. All right, this is called a disconnect. This is called a disconnect switch, sometimes called a safety switch. All right, in this case, this switch has fuses. All right, you can see there it says fusible 30 amp. This is for a 3-phase system. It's indoor, meaning the machinery that gets hooked up to this cannot be outside. Let me just pop that open, and we'll do an even more zoom in on it. These little setups right there, where you see the clips in that black base, those clips right there, sorry for moving them up and down, I'm trying to highlight that clip and that clip, will house fuses, meaning fuses will go in here. And the fuses are of the size maximum 30 amps, which means, and this is just something about these switches, you do not have to write this down or anything, but those switches can accommodate 5 amp fuses, 10 amp fuses, 15, 20, 25, and up to 30 amp fuses. That's what it means when those switches have that. Because, I know, it's a switch, and a switch is part of the branch circuit. However, because this switch has fuses, it is now an overcurrent protection device housing. Therefore, give myself a page here. Don't write this down. I'm just complicating it for the fact of complicating this, but we are going to talk about this switch coming up a little bit later. So I just want to mention it now, and you will also see this switch in other modules continuing on through the school. But this disconnect switch, let's say it's a 2-pole, A phase and B phase, and we head over to this. Let me change the conductor wires to keep them A phase, B phase colors. And we head over, I'm not going to draw it that big, make it a little smaller, to this disconnect switch. And now this disconnect switch feeds our, let's say, air conditioner that sits outside. Because there are fuses in here, now this changes things. These wires here now become feeder wires in the same way as the wires going to the sub panel were feeder wires. And now the branch circuit wires are here. So let's just make this easy. If the wires are leaving an overcurrent protection device, you can start writing this down already. I'm going to give you this note on the fallback on the other page, not on this illustration. If the wires start at an overcurrent protection device and end at an overcurrent protection device, they are feeders. No matter what the overcurrent protection device starting point looks like and what the one where it landed looked like. This one being a breaker, these being fuses.
Could you repeat that?
Yep. If it starts, if the conductors, let's go back even one more. If the wires are conductors, however you want to write that down, I'm going to put wires just for shorten that up. If the wires start at an overcurrent protection device and end at an overcurrent protection device.
OCPD, right?
Yes, OCPD, yep, very good. Those are feeder wires. Starts at an OCPD, ends at an OCPD, feeders. We don't need the note for the other one because we've already got that one. Starts at an overcurrent protection device and ends at a load. So going back one, I'm going to now add that here. But just to keep the illustration. All right, same thing if I'll just put it over here. All right, we have some wires leave here and go to the sub panel. All right, now originated at an overcurrent protection device, ended at an overcurrent protection device, feeders. Originated at an overcurrent protection device, OCPD, let's just shorten that up. Originates at an OCPD, ends at a load, branch circuits. Because there's just going to be different OCPDs out there. Right now, you are very used to breakers, and you're getting introduced to fuses. There was a, if you haven't seen that before, the disconnect where it houses fuses. It's a way to protect going back one. This is a good one for, right, that little spot that you see right there provides a perfect place to put your lock for lockout and tagout. Whenever you work around a lot of machinery, this is why they call it a safety switch. All right, this has to be provided for motors, so I'll put it this way again. And I'm putting it here now, so it's in the video, so if anybody comes back to the video later. Starts at ends. These are feeders. Okay, slide that up just for space purposes. I know sometimes that bottom right corner can have something that you might not be able to see it. All right, so now we understand what the branch circuit is. The wires that, we can look at this in two ways, because I'm gonna use the term sometimes the wires that, and I might just say the circuit that. The circuit that starts at an overcurrent protection device and ends at a load, or sometimes we're talking about those particular wires. In Article 210, we'll get into the wires. In Article 215, we'll get into the wires that feed between two overcurrent protection devices. But now we have the definition that separates the two. So if ever they get thrown into a warehouse with a bunch of different machines and things that you haven't seen before, and you're trying to figure out conductor size, because there is a whole rule set to sizing wires for branch circuits and sizing wires for feeders. This is one of the major reasons why these two things get separated. Because at the end of the day, there's just wires. But when you're sizing wires for feeders and when you're sizing wires for branch circuits, we have to approach that in two different ways. And there's a bunch of different things also that come with that. Different code sections that I have to use, etc. How to size the ground to these things, how to size the neutral for one versus the other. So it, dominoes into a bunch of other things. So if you're ever somewhere you're not understanding, you're trying to figure out what the wire is, just use this definition. Starts at some kind of protection device. It could be a breaker. Goes to a machine that has fuses in it. Then that wire between those two OCPDs is our feeder wires. Even if it ends at a load machine, but the machine has fuses in it, this is OCPD to OCPD. All right? Not to get too far down the rabbit hole of how confusing this could be, but to give you one where it can be a little bit complicated to understand. All right, for the rest of this module, we're going to really focus on residential branch circuits and outlets, but eventually you guys in 2 modules you'll be in Code D, where you'll start talking about industrial machinery, and in motors you'll be focused on motors. All right, let's see if I got anything else here. All right, has anybody got a follow-up to any of this? I think we've covered pretty much all bases. All right, so good. So I can show you some pictures. Maybe tomorrow when we get in, we'll do show you a couple pictures of a few things, and then we'll be able to identify which is which. All right, good. So as I said, I'll get rid of that. Here's the definition for these. All right. Also wanted to make sure that you guys understand what these are as far as, where we're going to see these. So what is an overcurrent protection device? I've said it now a few times, but OCPD is what you're going to read a lot, my Colt book and stuff like that, and me just in general using it. So I want to make sure everybody knows and has the definition for it. But there's a little bit more to this. So looking at the definition, and again, these points, definitely write this down. It's going to come up here and there. So an OCPD, or overcurrent protection device. All right, I can spell that out, but mainly current is the real focus here, because you'll notice it's not an over voltage protection device. It's not an over wattage protection device. It's not an over resistance, just to throw in resistance, the least used of the Ohm's law. This is my least concern, is resistance, until we get to voltage drop. But what this device is protecting us for, which is why the definition says it the way it is, a fuse or breaker that is rated, and rating is the amperage, or the amp rating. The code calls this, which I'll put here, ampacity. All right, there is a word for amp rating, and it's called ampacity. You'll hear this term used a lot. The ampacity of the conductors, the ampacity of the breaker. The ampacity of the conductors is the amount of amperage that wire can hold, or carry, or deal with when you turn on the load. The ampacity of the breaker is the amount of amperage the breaker can hold. Breakers are easy because they give us the number on it. Wires are a little bit difficult because we have to find them, which we'll get to in Article 310. So that's what that is. An overcurrent protection device is a fuse or a breaker that is rated to handle the amperage current of the circuit. So whenever you're sizing a breaker or a fuse for a circuit, what you're worried about is the load of the circuit. Right? The breaker is rated for the load that will be. Now, you don't have to write that down because we're gonna get into this in Article 220 and in this article as well. We'll start to talk about that. But I do want to talk about this for 1 second, which is load. I want to make sure everyone understands what a load is. A load is, well, we can get really technical and say a load is anything with resistance that gets plugged in. So let's not go that route. But a load is anything that is going to use the electricity to do one of only a few things that we can do with electricity, which is create light, create heat, or create motion, and also sound, but sound for us is sometimes not so much. These are the three main ones. We create light, we create heat, we create motion. Motion motors, heat resistors that heat up the water for a water heater, and light. So that's what a load is. A load is anything that is going to use the energy up. So, for example, the breaker is not the load. The wires are not a load. The outlet is not the load. There is no load here yet. In fact, this circuit would be said to have no load on it. How do we measure the load on a circuit? We try to get a amperage reading on the circuit. This is where our clamp on amp meter, digital multimeter is the one you guys use with a little clamp on it, comes into play. We measure the amperage of the circuit. So let's now unpack that a little bit. How do I know what's going to get plugged into this outlet? I don't. Right? There's an outlet right there on that wall. Can I plug in a compressor to that outlet? Yes, I can plug in a compressor to that outlet. Could I also plug in my refrigerator at the same time as I'm running my compressor? Yes. And I can also plug in an air conditioner if I put a power strip. In other words, I could load this circuit more than it is rated for. So the job of the overcurrent protection device, because it is rated to handle a specific amperage, is to open, trip is what we call it, but open in a case where somebody has put in too much amperage on the circuit. That is why current is the focus. Amperage or current, however you want to say that, is heat. That's what it is. Amperage creates heat. Technically, what it's creating is a magnetic field around the wire. It's creating a magnetic field. And it's like that. It's in a circle. That's why the clamp goes around in a circle. And the clamp is just measuring the intensity of the magnetic field. This magnetic field is creating heat. All right, one thing that we will get into when we get into selecting wires for circuit is how many wires did I put into this conduit? If I only have 2-3 wires, no problem. If I have 20 wires in there and all of them have amperage, I have a lot of heat in that conduit. So I have to make some considerations for that. Wattage does not create heat. Voltage does not create heat. Resistance does not. Technically it does, but it's the amperage that we're rating. So that's why this device is called an over amperage protection device. Not concerned with anything else. So as we get into the rest of this article, at some point we were going to run into having to size breakers or fuses, OCPDs in general, for particular circuits. Sometimes we know what is going to be connected to the circuit, like a motor that's going to be outside for the pool pump, like the air conditioner that sits outside, like the washing machine, like the oven. Sometimes I don't know, like the hallway, like the living room, like the bedrooms. So we're going to make some general purpose assumptions. In the code does give us a step-by-step on how to get here, but we're going to make some general calculations to figure out what size breaker has to feed this circuit, and then we're going to have some rules for specific loads, like the oven, like the dryer, like these days the EV cord that we have to put now for everybody's electric cars, that who knows if everybody's even going to have one, but they're now putting them in every house. You got to have a EV outlet. New construction. If it's old, doesn't matter. So that is what an overcurrent protection device is, and also that is what a load is. All right. So make sure as we just use this term, load, load, load. You're gonna hear this term throughout this entire set of this module. The next one, motors, PLC, not so much, but PLC is a whole different system. All right. Any follow-ups here? Anybody got an extra question here? All right. Good. So far, so good. Okay. So I'm going to fall back now for a second before we get into this next part. We're going to go look at the code book again. All right. So let's come over here. This code section starts at 210.4. The stuff above is completely, it's not irrelevant. It just goes into a broader thing that we don't have to concern ourselves with, like reconditioned equipment and stuff like that. We don't have to concern ourselves with that. So let's start here. Article 210.4. All right, as we do this code stuff, let me just kind of give you guys some pointers. You might not have a system yet. You want to have a system on how you highlight or emphasize something in the code book. I recommend highlighters, but here's what I usually tell people to do. Because you can do this. For example, you can just go, all right, this is something we're going to talk about. I'm going to highlight the whole thing. The problem is when you go to this code section to figure out, where or try to answer something, you might go, well, where is the answer? So another thing that you could do, for example, is simply highlight the article 210.4 and then highlight specific things within it that could be important. And then, for example, sometimes there are things within it that are not important. So truly, there's nothing in here that I would say you need to highlight because an answer is going to come from it. But you do need to understand that Article 210.4 will be somewhere that answers are going to need to come from. It could be in B, it could be in C, and it could be in D. It will be, but just giving you that idea. So sometimes just, again, highlighting the whole thing might not be the way to go. Highlight just specific things within it. Now, having said that, please use any system that you like, but this is the one that I have noticed worked for me, especially when you go back and have to answer a bunch of questions. All right, so this article is talking about 210.4 multi-wire branch circuits. And so the general says, branch circuits recognized by this article shall be, and again, anytime the code book says shall be, it is mandatory, shall be permitted as multi-wire branch circuits. So let's look at that one more time. Branch circuits can be multi-wire branch circuits. That's why the definition is coming up. A multi-wire branch circuit shall be permitted to be considered as multiple circuits, except as permitted in 30.3b, subsection 4, and this is simply talking about parallel conductors. Let's ignore that for a little while. We'll talk about them a little bit more in Article 215. All conductors, and here is something that I would highlight. At this point, here is what I would highlight. All conductors, and by the way, sometimes it's hard for me to highlight on this PDF. Just, there we go, that was okay. But you notice it didn't grab the end. There we go. Sometimes it just does some weird highlighting like that right there. So I'll tell you where it starts. All conductors is where I would highlight to the end of this. All wires of a multi-wire branch circuit shall, again, must, mandatory, no option here, originate from the equipment containing the branch circuit over current protection device or protective devices. In other words, all of the wires for a multi-wire branch circuit must come from the same panel. That is what that is telling us. Now again, in residential, it doesn't matter. I only have one panel most of the time. Sometimes there's two, but they're right next to each other if there is. And that is only because panels go up to 42 spaces, and big gigantic $1 million homes or more, $1 million, that's like a regular house in LA now. They're, $10 million homes, giant houses, can have a lot more circuits. So Sometimes you need more than 42 spaces. If you get into a commercial building, this is where that rule sort of also comes into play. Because I could have multi-wire branch circuits, I can have two different panels right next to each other, and they don't want one wire and the other wire for a multi-wire branch circuit to come from two different panels. Let's first get into what that is, and maybe that note right now is not making sense, but it will in a second. So what is a multi-wire branch circuit? Here's the note, and again, this is a note you want to grab. A circuit consisting of two or more, that is going to max out, by the way, I don't know why they say or more. This is 2 or 3. We only have single phase or 3 phase. There is no other system. There's no 4 phase, 7 phase, or any of that. So, but 2 or more is fine. So a circuit consisting of 2 or more ungrounded HOTS, ungrounded conductors with a common neutral, if applicable. We're going to unpack that a little bit. I'll go into different systems of multi-wire branch circuits. Example, and here are some voltages that you need to start to now get familiar with. All right, I will underline this one. This is residential. This one in green and this one in green are commercial industrial numbers. 12208, 12240, 277,480. What voltage comes into a building or house, residential, sometimes called a dwelling unit? What voltage comes into a building, structure, residential, etc., depends on the outside transformer. All right, the transformer that will feed power into the building. All right, you will get into transformers more in Code D and understand them a lot better. But just to give you an idea of what a transformer is, the utility company wires that are on the pole outside have to travel very long distances to get to your house, right? You don't have a power plant on the other block. Your power plant is miles away from your house. Hopefully.
Mr. Perez?
Yes, go for it.
For the 122, for the green, is it commercial or is it industrial?
122, the green one?
Yeah,
Yeah, this is commercial and industrial.
commercial and industrial.
Yes,
Okay.
the same as 277, 480. This is commercial and industrial. By the way, let's just make sure we all understand what commercial is. Commercial is a commercial building where the general public can walk into it. An industrial building becomes a place that either manufactures, distributes, or assembles. So, two examples, one versus the other. A Walmart is a commercial building.
Okay.
The Walmart distribution center is an industrial building. So, utility company wires, the wires that you see on the telephone, they used to call them telephone poles, on the poles, they have to be very high voltage because they're coming from very long distances. I remember what I said, and always remember this: distance equals resistance. The further away the originating voltage comes from, the further away the load is, the more resistance that we're going to have to deal with. So the electrical company just jacks up the voltage to really, really high numbers so it fights through all that resistance. But before it gets into your house, it can't be 12,000 volts. They got to step it down to one of these numbers: house, commercial building, industrial building. So these are the 3 most common numbers that you will find. There are some other ones. When you get, like I said, to Code C, you'll look at some other different numbers, just a couple, all right? Some different combinations of these, all right? Because there's like a 240, 480, so we don't have to get into all of them, but here are some standard numbers. So, a multi-wire branch circuit. So what is a multi-wire branch circuit? Well, it is exactly what it says it is. There's more than one wire. One of the conductors that you guys have used so far is a 12-3 Romex, right?
Yes.
Where you have hot, other hot, and you have neutral. Okay, so we'll get rid of that. Here is the example of a multi-wire branch circuit. I'm going to use a fresh page to do this because I'm going to illustrate a couple of different ones. So here is a multi-wire branch circuit. Panel. By the way, I'll pause at the end of this to give you guys a chance to take a picture. Always keep in mind there's going to be a follow-up video. I have one breaker, 20 amps. I have breaker number 2 here right below it. Sorry, I wanted to make it about the same size. 20 amps as well. I have one conductor going to this outlet here. I have the second conductor in my Romex going to this outlet here. And the neutral is being shared between both of these circuits. So this is an example of a multi-wire branch circuit where the neutral is in play. Always ignoring the ground. The ground is not part of the circuit. It's just the safety that comes in. So I usually don't draw the ground. So this is an example of a multi-wire branch circuit. 2 wires plus the neutral going to this outlet. Now this is legal, and we'll get into a few rules that the code has to, that we have to follow. So let's pause here for a second and go look at this first little rule that we have in 210 for B. Disconnecting means. It says each multi-wire branch circuit, like the one I've shown you here, 1 breaker, 2 breaker, must, no option, must be provided with a means that will simultaneously, that is a big word here. It used to not say this. This is a big change the code book has made. Each multi-wire branch circuit shall be provided with a means that will simultaneously, at the same time, disconnect, heading on up, all ungrounded conductors at the point where the branch circuit originates. Remember, that just means panel. So, that rule now says that these 2 breakers have to shut off at the same time. All right, I'll pause there for 1 second in case there's a follow-up.
How do you?
There's the follow-up then. How do you do that? Very good. So first, let's just acknowledge the rule, right? If these 2 breakers, and this is what the problem becomes. The problem becomes here. We are sharing this neutral. So let's go back 1, and then I'm going to get into the how. If I plug in a load, remember right now, nothing is plugged in. There is no amperage, right? There's no current right now. The current that we would measure on any of these wires, that's the other thing to keep in mind. The hot can have amperage, the neutral can have amperage, because this is AC. Everywhere is the same, meaning if I check the amperage here, here, or here, I can effectively start reading some common numbers, but there will be some differences, and I'll explain here in 1 second. So if I plug in a load into this outlet, and let's say this load, when I turn it on, generates 15 amps, whatever it is. Say I plugged in a refrigerator. And this load over here, I only plug in a lamp, right? Just a little lamp, not drawing a lot of amperage, let's say 3 amps. So, and I don't know if you guys covered this in Code A or not, but it's something important that you have to understand about this circuit right now. Does anyone know how much amperage this neutral will have? Now, as I'm asking that, you're probably going, well, it probably isn't 18 because I'm going to guess he's asking for a reason. Right? So it's not 18. All right? It's not 18. This isn't part of this course, but since we are talking multi-wire branch circuits, it's important to understand this. The neutral is going to carry amperage back to the panel. First of all, that's what the neutral does. It used to be called the return because it's part of completing the circuit, getting the current back technically to ground. This is why you will get into this next module, but the neutral and the ground are bonded at the panel. Let's not go too far down the rabbit hole. The only job the neutral has is to carry the amperage back to the panel. However, when we share the neutral carries, and I'll put it here as a note, the unbalanced, we call it unbalanced load, but just because this is the first time you might be hearing this, I'll put it in another way that's a little bit more understandable, which is current. The neutral carries the unbalanced current, meaning that the amperage on this neutral is 15 minus 3. That's the unbalanced. So if I was to measure the amperage on this neutral, anywhere on this neutral, I would read 12 amps. By the way, if I balanced this out, meaning I had 15 and 15, then 0. There's a problem here. There is a potential very dangerous problem, which is why this rule simultaneous showed up. If I get rid of this, and how could I get rid of that? Well, I opened up a splice. All 3 of those wires were spliced at a junction box. Unbeknownst to me, because I was going to wire something else into here, I undid this wire nut and I separated these 3 neutrals from each other. Or I removed the neutral going back this way. Now where does the current go? There is no way out. The current goes into the loads. All right? The current finds its way into that load and that load. And here's the other nightmare of this. They are now 2 different phases, A phase and B phase, which are not supposed to ever come into contact with each other. They are now part of returning or backfeeding into those loads. So we will destroy whatever is plugged into this outlet. All right, that's one nightmare here. The other nightmare here becomes if I'm in the way here. All right, if I somehow become if I, let's say for example, I'm working on this and I shut this breaker off, meaning there's no more 3 amps over here, everything here is now off. But everything here is still on. And guess where those 15 amps, this is alternating current, meaning it goes everywhere. And now this neutral on that other outlet that was supposed to be off is now potentially can have current. When can it have current? If again somebody disconnects this neutral. Working on the line, disconnected one breaker, want to take some wires apart, want to disassemble this circuit and do whatever to it. And now I've created a situation where I'm backfeeding current into a outlet that the electrician thought was off, and now potentially they can get shocked. And of course, amperage carries the part that will kill us. So this is where simultaneous showed up. If you want to shut one breaker off, you shut both off at the same time. And now to answer the question, because we'll wrap up here in 1 minute, we'll pick up tomorrow where we left off. To answer that, they sell a clip. All right, so on the side of a breaker, and I'll just illustrate this. If you look at a breaker, and I'll try to do a little bit of 3D action, which I'm a semi-decent artist. On the handle of a breaker, this is the handle of a breaker, and you can go look at it tomorrow. There's a little hole here on the handle of the breaker. If I put two breakers side by side, both having that little hole, then they sell a pin. There is an actual factory pin that goes through here. It has like this kind of little square here, it goes through the other one, and now I've tied both of these breakers together. You could also do this with a number 12 solid if you don't have this pin. All right, something that we do in the field a lot. This little pin will be solid, and it'll go through both breakers. And now, physically, if you shut one off, that pin takes the other one with it. If one breaker is the other thing that can happen, this breaker trips for whatever reason, whatever was on this circuit had a short circuit, a ground fault or something, causes the breaker to trip. They both shut off at the same time, and we don't get that scary neutral effect.